The intermediate value theorem is an important theorem in calculus, and it talks about functions that are continuous over closed intervals. Functions that are continuous over closed intervals have many useful properties, and we'll begin examining that today. So first, to use the intermediate value theorem, we're going to have to make sure that f is continuous over a closed and bounded interval, a to b. So that would mean, bounded would mean that a and b are fixed points, fixed values, specific values, not say like infinity or negative infinity. If we have that, a function that's continuous on our closed interval, then we can look and see what would be happening with the function. So b, we could come up here and find a point on the graph, and that would correspond to a value in the range, f of b. And we could do the same for a, and that would correspond to f of a. So we would have some interval in the domain, a to b, that corresponds to some interval in the range, f of a to f of b. What the intermediate value theorem tells us is that I can pick any value in the range between f of a and f of b, let's call that z. I can pick any value, and what the intermediate value theorem guarantees us is that I can trace that back and find a specific value in the domain, we'll call that c, that corresponds to z. And moreover, it says that that c will be between between a and b. Another way of saying this is that for every output of the function, on the interval, so for the outputs we're talking about a value of the range, we can find at least one value in the domain, at least one, let's say corresponding value. So a few things to note here is, one, this is just an existence theorem. It just tells us, that C exists, that this value in the domain exists. It doesn't tell us how to find what that value is. And two, we should note that there could be more than one value of C. It's possible. Okay. For example, if I had picked z down here, then there would be a c value here, and well, that one looks like it's a little bit less. So if we had picked a little further behind, so it could be that there is more than one. So let's use the intermediate value theorem to determine if the following functions have a 0 on the interval. So what we're talking about when we have a 0 is we're asking where is it that the function value is equal to 0. And a good place to start to answer this is to evaluate. We're given the interval is from negative pi to pi. Let's evaluate the function at the endpoints. You could also evaluate it at any point in the interval, but the endpoints are a nice place to start. So let's take the function and evaluate it at negative pi. And when we simplify this, we get minus pi minus, well, the cosine of negative pi is minus 1. So this becomes minus pi plus 1, which is an irrational number. This is the exact value of it, and it is a negative value. Now let's evaluate the function at the other endpoint. That is at positive pi. When we do that, we get pi minus a minus 1, and in this case that's pi plus 1, and this is positive. And this is exactly the results that we were hoping for, so that we can show that there's a 0 on the interval for f on the interval between minus pi and pi. So what we can say then is, since f is continuous on the interval negative pi to pi, and we know that because x is just a polynomial and the cosine of x is just a polynomial, or I'm sorry, as a trigonometric function, and the combination of those will be continuous on their domains. And they both have domains that are all real numbers. So of course it will be continuous on negative pi to pi. So since f is continuous on negative pi to pi, and f of negative pi, the endpoint, is less than or equal to 0, which is less than or equal to f of positive pi, okay? Because this is a positive value and this is a negative value, then we've picked z to be equal to 0 because we're looking for where the function equals 0. Then, by the intermediate value theorem, which we just abbreviate IVT, there exists a C, there exists at least one C, in A to B, such that if you take the function and evaluate it at C, you will get to 0. Again, I don't know how many C's there are that corresponds to this or where that C is, but the intermediate value theorem does guarantee its existence. So let's try another one. Let's work with g of x this time. So oftentimes what we will do is we'll jump straight away to evaluating the endpoints, and we get g of x as g of negative pi is negative 1 over pi, and clearly this is negative. And if we take g of pi, we get 1 over pi, and clearly this is positive. And what students are tempted to do at this point is to say, well, then there exists a 0 on the interval from negative pi to pi such that 1 over x is equal to 0. This is not true. We have to be careful about how we're applying this theorem. Remember, f must be continuous. On the interval, negative pi to pi. Okay. So if we look at the graph of this function, 1 over x is just our simple rational function. It has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. It's bounded in the first quadrant here and in the third quadrant over here. Okay. Here's negative pi and here's positive pi. And what we can see now is that very clearly there is an infinite discontinuity here. And because of that, we cannot apply the intermediate value theorem. So be careful.